Hi everyone, Assalamu alaikum. So, how many of you guys here? 45. Okay, so I think we can um, proceed with our class today. So, today we are going to continue our module 2.1, okay, that we stopped last week. And this week we are going to start with our lab session. So starting this week we will have the lab session. So for the link for the lab session, we're gonna use the same link. The link that we are using right now for our lecture. Okay, we are going to use the same link. So you just simply go to Google Classroom and join from that link. Okay, so and then all the recording for our lecture and our lab I will upload on Google Classroom. Okay, some of you that just joined this class, and I welcome you guys. And uh, so okay, let's get started with our class today. I hope you guys can see my screen. So please remind me by the end of this lecture to share with you the attendance link. Okay. All right. So let's get started. So last week we have studied about few problems, right? 4 problems, but we haven't touched about the algorithm on how to solve the problem. So that is what we are going to learn this week. Okay, we are going to learn about the algorithms. Okay, all right. So these algorithms, it falls in this group that we call as uninformed search strategies. Uninformed search strategies, that means you are not informed with details information. Okay, so uninformed strategies definition is basically, let me full screen. Okay. So this is the definition for uninformed search strategies. Okay, it uses only the information that available in the problem definition. These strategies order nodes without using any domain specific information. Okay, strategic order nodes. Okay, so we are going to have to learn several techniques today. Okay, we are going to learn about breadth first search, the uniform cost search, the depth first search, the depth limited, the iterative deepening search, and the bidirectional search. Okay. Okay, let's take a look at the basic search algorithm in the uninformed search. Okay, so the breadth first search. Okay, breadth first search, the short form, the acronym for this algorithm is BFS. Okay, BFS. Okay, so breadth first search. Okay, how did you do that? You go from one node to another node. Okay, so breadth first search is basically a simple binary tree by a marker. Okay, so basically for this algorithm, you expand all nodes at depth before expanding at depth I plus 1 level or the traversal. Okay, and then for this leave first. Okay, that's what we call as first in, first out. Okay, notes visited first are expanded first. Okay, the notes that you visit first expanded first. For example, let's take a look. We start at A. Okay, we start at A. And then we visit whichever that we visit first. If we visit B first, that means we will notes visited first are expanded first. So we go to B, and then what is the note after B is D and E. And then after we're done with B, then we go to C. And then we expand C, and then we saw C have F and G. Okay, that's what we call, that's what it means by notes visited first, expanded first. So new notes, which are always deeper than their parents, go back of the queue. Okay, and old notes, which are shallower than the new notes, gets expanded first. Okay, like for example here, let's say E. E is the child to B, but E is the child to B and B is the child to A. And then what? E have deeper notes compared to A. Okay, so parents always have shallow notes. Okay, alright, so the NQ notes is in first in and first out order. Okay, that's what we call, that's how BFS algorithm works. Okay, this is the pseudocode for BFS algorithm. Okay, you can see here first you mention the initial state. Okay, you mention the initial state at the beginning of the initial state, the path cost should be equal to 0. Okay, because you haven't started searching the nodes yet. Okay, once you go to the first one, this is the path cost is 1. When you go to the third level, the path cost is 2. Okay, alright, so the BFS algorithm will be considered as complete if the shallowest goal node is at some finite depth D. Okay, so the breadth first search will eventually find it after generating a shallower node. That means it will try to find the shallowest node, the closest path, like our previous example that we go through last week, right? So we're trying to find the shortest distance from Arad to Bucharest, right? So from Arad to Bucharest, we found the shortest distance by passing two cities. Okay, that's what we call as the BFS algorithm. We try to find the shallowest node, the shortest. Okay, all right. So this is how, for example, you have this example. Okay, for example, you want to go to J. Okay, you want to go to J. Which one is the shallowest distance? Okay, first you have to elaborate. Okay, from A. Okay, first you go from A, and then the breadth first you have to expand the first one, right? Okay, you go to B, and then B expand to D, to D, and then D go to H is already failed because that's not the goal. Okay, and then you reverse. Okay, from D you go to E. Okay, from D you go to E. Okay, and then from E, is this the goal? Is this the goal state? No, it's not the goal state. Okay, so you from E you go to J, and then you have successfully found the J, the goal state. And on the other hand, how about the F? The F1, if we want to find the F node. The F node we go to A first. But when we expand B, we will not find F, right? But when we expand C, we go to C, and then we will find the F. Okay, all right. So we are trying. It depends on the cases. It depends on the problem that you have given in order to select the best algorithm. Okay, so let's take a look at this first example. Okay, given the following state space, okay, tree search, okay, give the sequence of the visited nodes when using the BFS. Assume that the node O is the goal state. Okay, the node O is the goal state here. So how can you do? If you do, where can you start? Obviously, you start from A, right? Okay, when you start from A, okay, you go to B first, and then you go to B, and then what? Remember the definition of BFS algorithm? Nodes that have visited the node that we visited first will be expanded first. Okay, so we expand the node B here. Okay, we expand the node B, so B have F and G. All right. And then after that, we go level by level. Okay, level by level. And then now we go to C. C, we expand the C to H. And then we go to the third one. Okay, this right now we are at level 1. Okay, we go to D, and then D have I and J. And after that, we go to E. Okay, E doesn't have any nodes after it. Okay, and then we move to the second level. Okay, we expand the F. We expand F, but F doesn't have any nodes connected to it. So we expand the G, and then we expand the H. H also empty. We expand I, we expand J, and then after that we expand K. Right now we at the third level. Okay, third level we expand K, we expand L. Okay, so from the question we want to know the path to go to O. Okay, this is our goal state. This is our initial. Okay, this is our goal, which is O. So now we know O is the child to node L. So we have to find the path to go to O. Okay, and then we expand M, and we expand N. And then the goal state here is O. So the return solution that we can write is from A, we go to B, from B to G, G to L, and L to O. That's the solution for this problem. Okay, easy, right? It's very easy to understand. Okay, that is it about BFS. Okay, now let's take a look at the Romanian holiday example that we already went through last week, right? So in this example, for the Romanian holiday, we have to find the path, okay, from Arad to go to Bucharest, and then we have came out with the solution last week. We go through Sibiu and Fagaras, passing only these two cities in order to get to Bucharest. Okay, but how can we design this problem? Okay, if you are given this problem in a form of map like this, how can we design this problem to make it to be as the tree like this? Okay, so normally if you are given this problem, first thing you have to do is transform it into a tree. Okay, transform into a tree. So we start with Arad. Okay, we start with Arad. And from Arad, where can we go? Okay, from Arad, where can we go? Okay, we go to Zarin, we go to Timisoara. Okay, so now we added. Oh, yeah, one more. Timisoara, Sibiu, and Zarin. These three cities that connected, especially connected to Arad. Okay. Then, so we draw. Okay, we have Arad connected to Zarin, Sibiu, and Timisoara. Okay, and then from Zarin, where can we go? We can go from Zarin to Arad, but we don't want to put Arad because that will be reverse. Be reverse destination, right? We want to go straight to Bucharest. So Arad and Oradea. Okay, so how about Sibiu? Okay, Sibiu, from Sibiu you can go to Arad, Oradea, Fagaras, and Rimnicu, Vilsia. Okay, that is from Sibiu. Okay, and then we have Timisoara. Timisoara can go to Arad and Lugoj, but Arad we shouldn't include Arad because it will be reverse. Okay, so Lugoj. So from this part, we already know the results from last week, right? We go from Arad to Sibiu. Alright, so how about the puzzle example? Okay, so this is the initial state for this example. Okay, we have the initial state where the empty box is located at the bottom rows in the middle of the bottom rows. How can we move the empty box to be in the middle of the puzzle? Okay, we want to achieve this. This is the goal. We want the empty box to be in the middle of the puzzle. So how can we do it? So you guys have to show it step by step. Okay, so in a form of tree like this, you break down how many position is possible to move the blue box. Let's call it as a blue box. Okay, how many position is possible to move the blue box? Okay, so right now the blue box is at the bottom row, in the middle of the bottom row. Okay, you can switch the position of the blue box with number 7. Okay, it will be on the bottom left of the puzzle. And you can change the position with the number 6 to be in the middle of the puzzle. And you can also change the position with number 5, and then it will be on the bottom right of the puzzle. Okay, now you expand. Okay, you expand this first one. Okay, you expand. How can you move? You have to make sure that the numbers are in order. Okay, 1, 2, 3, 4, 5, 6, 7, 8, and the blue box is in the middle. Okay, you gotta do step by step, moving this blue box until it achieves the goal state here. Okay, so from this solution we can see that the middle one will achieve the goal state, where you move the blue box to the middle first and switching the position with number 6, and then keep moving the blue box to the left, and then after that move the blue box to the top left. Okay, and then switch the position of the blue box to be top and the middle, and then from top middle you can go from here to here, and then oh no, not this one. It's the, let me get the eraser. Where's the eraser? Okay. Okay, from here to the middle, change the position of the blue box with 6, and then change with number 8, and then from here, okay, and then we change the position of the blue box with number 2, okay, and then we change the positions of the blue box with number 1, okay, and then finally we will have the goal here, which is the number will be in order of 1, 2, 3, 4, 5, 6, 7, 8, and the blue box in the middle. Okay, that's how you solve the puzzle problem. Okay. Okay, that is BFS. Okay, now the second algorithm is about the basic search algorithm, the uniform search, uniform cost search, or the acronym for this algorithm is UCS, uniform cost. Okay, why it's cost? That's because we will calculate the cost of each path, that the nodes, that how we expand the nodes, and the cost of each path, and then you will have to choose the shortest, the smallest number for the path cost. Okay, so the steps are quite similar with the breadth first search earlier. Okay, but in this one we care about the cost of the path. Okay, UCS takes into account the total cost. Okay, we want to choose the cost that have the smallest number. Okay, so UCS is guided by path cost rather than depth. Okay, all right. So the main idea in UCS algorithm is you are trying to expand the cheapest node. Okay, where the cost is the path cost. All right. Okay. So when are you going to assume this algorithm is complete? Is when UCS expand nodes in order of optimal path cost. Okay, then you can consider as a complete cycle. Okay, so this algorithm very good because it will give the shortest distance and also the shortest cost. Okay, let's take a look at the example. You will understand more. Okay, so now we have the goal state here is the goal state. So no, okay, first we have the cost for each path. Okay, we have 5, we have 2, 1, 4, 1, 7, 4, 5. So now you have this tree, and then you are given this path, and now you are going to find which one has the shortest cost. Uniform cost search. That means you want to find the path cost of node n. Okay, so you go to the end of each node. Okay, and then you calculate how much the total number of each node. Okay, for this one, from this node to this node, okay, you have 5. So this node cost is 5. And then go to the last one node here is 1. Okay, so this node cost is 6. Okay, 5 plus 1 is 6. And then let's take a look at this node. Okay, this node 5, and then we have the cost here is 4, and then this node is 9. Okay, and then we have this, move to this side. We have this node, this path 2. Okay, and then so this node value is 2. Okay, and then you move to these two nodes. Okay, this node have the value of path is 1, so it becomes 3. Okay, 2 plus 1, 3. Okay, and then how about this one? This one is 2 plus 7, 9. Okay, 9. Okay, and then how about this node? This node is, okay, we have 3 here, right? 2 plus 1, and then we have the path cost here is 4. So 3 plus 4, it becomes 7. 7 for this node. And then for this one is we have 3 plus 5, 8. Okay, 8. So compare all this. Which one is the smallest? So the smallest here we have is 6. Okay, so that is your goal state because it has the smallest cost compared to others. Like this one have 9, 7, 8, and 9. Okay, this one is the smallest one. Okay, all right. This is just okay. So now I want you to do some exercise. Okay, all right. So we have this Romanian holiday. We have this Romanian map. Okay, we want to go from Arad to Bucharest. I want you to calculate what are the distance and what is the value of the shortest distance with the lowest path cost from Arad to Bucharest. I want you to calculate all possible routes and which one have the smallest path cost. I give you 10 to 15 minutes to get this done. Then I will call any of you guys here, any of you guys in this chat room to tell me the answer. Okay, you can start to do the exercise now. Sure. So, did any of you guys got the answer? Okay, yes, the shortest with the lowest total cost. Dharmasilan, you got it? 418. Okay, 418 from which route? Can you mention the city name? Okay, that's correct. Thank you. So is like your friend said earlier, the shortest path is 418. 418. So from Arad to Sibiu to Rimnicu Vilsia to Pitasti and to Bucharest. Okay? But remember at the BFS, when we use the BFS algorithm, we got the Sibiu, Fagaras, and Bucharest, right? Because we were trying to find the city that to find a path that pass by less cities. But now if you calculate from Sibiu, Fagaras to Bucharest, the total path cost is higher compared to Arad, Sibiu, Rimnicu Vilsia, and Pitasti. Okay, this one only for 18. Okay, so let's proceed. Okay. Okay, now for those that haven't got it, you can try again after class. Okay, try to get the value of. So, yeah, this is just the explanation. Okay, so let's take a look at the. We already take a look at BFS, UCS, and now we move on to the third one. Third one, which is the depth first search, or the short form for it is DFS. Depth. Depth is how deep the node can go. Okay, depth first search. Okay, that means from the name itself, you can tell that this algorithm is looking for the deepest node. Okay. Alright, so the main idea for this algorithm is you expand node at the deepest level. Okay, so we are starting from left to right. Okay, the search proceeds immediately to the deepest level of the search tree, where the nodes have no successors. Successors here, that means the node have no child. Okay, it keeps going to the deepest level. So the implementation of this, we use last in first out queue or stack, or the short form is LIFO, last in first out. So it enqueue nodes in LIFO, last in first out order. So let's take a look at the example here. Okay, like this one, it will go to the deepest one from A to B to D to H, and H doesn't have any successors nodes. Okay, and then it will go from the reverse to D, reverse to E, and then go to J, and then go to I, and then from I reverse to E and go to J. It goes to the depth first. You search the goal state by going to the def first node. Okay, that's how you do it. Okay, now let's take a look. Okay, so we have this tree. Okay, you are given this tree. Okay, so the def first search on a binary tree. Okay, we call this as the binary tree. So the unexplored region is shown in light gray. Okay, the light gray is the nodes that we haven't go yet. Okay, and then the explored nodes with no descendants in the frontier are removed from the memory. So that means nodes that have no descendants, it will be removed from the memories. Okay, and then nodes that has depth 3, that means that 3 level depth, have no successors, and M is the only goal node. Okay, this is the story for this example. Okay, M is the only goal node. Okay, so how can we go from A to our goal here, which is M? Okay, so see how that first algorithm works. Okay, so we start at A. Okay, we go to B, and then from B we go to D, and then from D we go to H. Okay, H doesn't have any successors node after it. Remove H. And then it go to I. I doesn't have any successors. Successors mean the node connected to it, right? Child. Okay. I doesn't have any successors. Remove I. And then we go to E. Okay, from E we go to J. Okay, J doesn't have any successors. We remove J. And then we go to E. Back again. And then we go to K. K doesn't have any successors. We remove K. And then now we go back to C. Okay, because on the left side are done. We already look at the left side. Okay, so now we remove K, right? And then E will not have successors. We remove E. So now once we remove E, B will not have successors. We remove B. So now we have the right side of the binary tree. Okay, now we go to C. From C we go to F. Okay, F we go to L. Okay, L doesn't have any successors. We remove L. And then F go to M. And then now we have arrived at the goal node. So the solution for this one is from A to C to F to M. Okay, so that's if you have a question given a binary tree. Try give a solution using DFS algorithm to achieve the goal node M. If you are given this binary tree and that's the question. Okay, that's how you do it. Okay, make sure when you read the questions for your exam, make sure you read carefully and make sure you are not confused with what kind of algorithm the question asks you to answer. Okay, because different algorithm you implementing will give you different answers. Like the Romanian holiday earlier, we can see already the difference. Okay, if you use UCS, it's different. If you use BFS, it's different. Okay, all right. So, second example for DFS. Given the following state space, the tree search, okay, get used to with all these terms, okay? State space, tree search, binary tree, okay? Don't get confused, same thing. So give the sequence of visited nodes when using DFS, okay? Assume that node O is the goal. So like this example that we did earlier, we go to the deepest and we remove the one that doesn't have successors, right? We want to achieve this one. So let's take a look. Okay, From A, we go to B first. Okay, B, we have two successes. Okay, F and G. And then from F, doesn't have any successes. Okay, we go to G. G have K and L. Okay, from G, we go to K. Okay, from K, we go, okay, and then G go to L, and L will get the O. So, O is the goal state. So, you get the answer for this one is A, B, G, L, O. The sequence for this tree. Okay, so let's take a look at this example again, the Romanian. Okay, so if we use DFS algorithm to find to go from Arad to Bucharest, what is the answer is gonna be? Okay, so from Arad, look, from Arad. Okay, Arad, it has Zarin, it has Sibiu, it has Timisoara. Okay, we have Zarin, we have Sibiu, and we have Timisoara. And then from Zarin, we have Oradia, and then we have Sibiu. Okay, and no, from Zarin, we have Oradia only. Zarin, we have Oradia, and then Arad again. Okay, so if you this example is not complete. So if you look at this, okay, you draw the tree, okay, from Arad, okay, from Arad, you draw Bucharest. Okay, the deepest one, if you look like this, I can tell you go from Arad to Timisoara, Lugoj, Meshadia, Dobreta, Grovia, Pitești, and Bucharest. That should be your answer. Okay, the deepest one. Okay, because you keep expanding the tree. Okay, so how about the puzzle? Okay, the puzzle, in order to achieve the goal, what will be the route? What will be the route? Earlier the answer, if we use the BFS, okay, if we use the BFS, you will have to go to the middle first, okay, and then move to the left, move to the top one. Okay, but this one is different. Okay, this one you change the blue box position with 6, and then you change with the 8, and then you change with number 2, and then you change with number 1 again, and then you will arrive at the goal state. Okay, all right. So different algorithm will give you different answers. So that's why when you answer the questions, make sure to understand which algorithm that the question asks you to answer. Okay, all right. Now depth limited search. Okay, the name itself limited. Okay, so it's similar to the DFS earlier. Okay, it's similar to the DFS, but the difference here is it has some limits. It has some limits. Okay, based on the name itself, it has some limits. And then the acronym for this algorithm is DLS. You guys can hear me, right? Okay. All right. So DLS, okay, it's simply DFS with a depth bound. Okay, you have a condition, depth bound. Okay, searching is not permitted beyond the depth bound. Okay, so it will give you the tree. For the DFS earlier, it just give you the tree. Okay, and then find the goal state. Okay, but this one, okay, find the goal state with the depth bound given. Okay, it will give you the depth bound. You cannot go as deep as you want. Okay, So it will work well if we know what the depth of the solution is. Okay, if you know, okay, the solution is on the third level of the tree. Okay, that will be easier. But if we don't know, that means your algorithm will be terminated. Okay, all right. So if the solution is beneath the depth bound, the search cannot find the goal. Okay, hence the search algorithm will be incomplete. Okay, otherwise we use the iterative deepening search. Okay, all right. So for now, let's focus on DLS first. Okay, so in DLS, the main idea is you expand the node at the deepest level, but limit depth to L. Okay, so what does it mean by limit depth to L? Okay, limit depth to L, it means, okay, let's take a look at this example. Okay, so given the following state space, give the sequence of visited nodes when using DLS, limit is 2. What does it mean by limit 2? Okay, limit 2, that means there are 2 levels. Okay, so right now if we're at node A, we is the limit equal to 0, node A. And then node B, C, D, E is limit equal to 1. Limit here is like how deep you can go. And each level of the nodes considered as one increasing limit. Okay, so here is 0, and then here is 1, and here is limit equal to 2. Okay, the questions want you to give the sequence of the visited nodes when you use DLS with limit 2. Okay, so we have the condition here, limit 2. Okay, now we start from A. From A we go to B. Okay, from B we expand to F and G, and then we go to F, and then we go to G, and then we go to C, H, and then D, go to IJ. Okay, and then from E we go to what? Failure, because E doesn't have any successors node here, so the algorithm fail because our condition here has to be limit equal to 2. Okay, so for that example earlier, the DLS algorithm will return failure. That means no solution. Okay, the reason is that the goal is beyond the limit. Okay, the limit here is 2, but the goal depth is 4. Okay, we want to go from A to O, but here is limit 3 and O is located in the 4th level. So you will never get to O because the condition of the depth for this one is only 2. So the algorithm will return failure. Okay, no solution. Okay, for depth bound trees, that's like this. That's how it moves. Okay, go to the deepest level, then to the neighbor nodes, and go to the deepest level. Okay, the depth bound tree. Okay, so that is DLS. Okay, now that was like our 4th one, right? 4th algorithm. Okay, now let's take a look at our 5th algorithm, which is the iterative deepening search. The iterative deepening search, or the short form is IDS. Okay, so for this one, okay, IDS return a solution or a failure for depth equal to 0 until infinity. Do depth limited search given the problem and the depth. If the result not equal to cutoff, then return the result. So for this algorithm, okay, it repeatedly applies depth limited search with increasing limit. That means it can increase the limit. It didn't stop at 2. The previous one, just when the question just give you the limit, you cannot go beyond that, right? But this one, it can increase the limit. Okay, it terminates when a solution is found. Okay, once they found the solution, okay, it will be terminated. Okay, or if the depth limited search return failures, meaning no solution exists. All right, so that's the definition for the IDS. So the key idea behind this algorithm is it will apply DLS repeatedly with increasing depth. Okay, so basically IDS, it combines the benefit of BFS and DFS. Okay, so that means the nodes on the bottom level, okay, are generated once. Those on the next to bottom level are generated twice, and so on, up to the children of the root, which are generated d times. Okay, all right, so let's take a look. The iterative deepening search. Okay, level limit equal to 0, only one node, limit equal to 1, you have, okay, 1 successors nodes, limit equal to 2, okay, you have 2 successors, limit equal to 3, you have 3 successors, that means 3 levels of nodes. Okay, all right, so limit, for example, you want to go to m here. Remember the example we had earlier? We want to go from A to M. Here, M is right here. Okay, so we start at A at the limit 0. Okay, A, does it have any successors node? Yes, it has B and C. Okay, now we visit B first, and then after that we visit C. Okay, once we visit B and C, what is the successors node for them? Okay, we generate D and E, F and G for C. Okay, and then we move on to the successors node for B, which is D. Okay, D. Does D have any successors? No. And then we go to E. E. Does E has any successors? Okay. Yes. Okay. Okay. And then we keep moving. Keep moving. Keep moving. Finish that level. Okay. Now we move to the limit 3. Limit 3. We start from the left to right. Okay. Go to limit 3. It keeps adding the limit for you. Doesn't matter. As long as you find the solution. The solution here, we want to find M. Right. Now we want to find M. So you go step by step, and then you are now at the limit 3. Okay, you go to F, and then when you're at F, you find L and M here. So that means you have found the goal state, okay, at limit equal to 3 when you use the iterative deepening search algorithm. Okay. So back to this example again, simpler compared to the previous example. So given the following state, give the sequence of the visited node when using IDS. Okay, when using IDS. So wants you to give the sequence. Okay, so you started from where? You started from where? You have to do one by one. Okay, first you do the DLS with bound 0. You go step by step. Bound 0, okay. You have A. Okay, limit equal to 0. Okay. And then fail because that's not where your goal is at. Okay, because you want to go to the 4th level, right? The O. And then you go to the DLS with bound 1. Okay, you go to B. And then you go to C. You go to D, you go to E, and then fail. Okay, because you have finished limit 1, okay, but you still haven't seen the goal. Okay, now continue with limit 2. Okay, limit 2, you go to B, F and G, C, go to H, D, go to IJ, and N, E will fail again because E doesn't have any successes. Okay, but we want to go to O, right? So we continue with bound 3. Bound 3, okay, we go from A to B, F, G to K and L. From K and L, we go to C, H, we go until all the way until limit 3. So, still fail, okay? So, now we tried with limit, with DLS with bound 4, okay? Okay, with bound 4, we go from F, G, K, L, O. Now we found the goal state. So, the answer is A, B, G, L, O, the sequence for the path. Okay. So, yeah, that's how the depth bound go. Okay, if you have one depth bound, you go to this level. If you have two depth bound, you go to second level. If you have three depth bound, you go to third level. If you have four depth bound, you go to the fourth level. It depends on the depth bound or limits, the similar things. Okay, similar terms. Okay, don't get confused. Okay, now this is, I think this is the last one. Okay, the bidirectional search. Okay, or the acronym for this algorithm is BDS. Okay, so the main idea behind this algorithm is to run two simultaneous search. Okay, to run two simultaneous search, start searching from both the initial state and the goal state and meet in the middle. Start searching from initial and the goal. Okay, so check whether the node belongs to other fringe before expansion. And the space complexity is the most significant weakness, and if complete and if optimal if both search are breadth first. Alright, so that one is like this lah. If you, for example, if you want to go to the goal node, for example, you have A, you want to go to D here. Okay, you will start searching from both sides. You will start searching from here. At the same time, you also start searching from here, and you meet here in the middle. Okay, that's how the bidirectional search works. Okay, so let's compare of all the search algorithms that we have went through. Okay, so we have breadth first, BFS, we have uniform cost, UCS, we have depth first, DFS, we have depth limited, DLS, we have iterative deepening, which is IDS, and the bidirectional search. Okay, so the most convincing algorithm and the most used algorithm is the IDS, which is the iterative deepening, because it is the most optimal and it guarantees you to complete the cycle and find the goal state. Okay, so an increasing order of effectiveness in reducing size of state space and with increasing computational cost. Okay, so first, these three things that you have to avoid when you are designing an algorithm. First, do not return the state that you just came from. Do not create the path with cycles in them, and do not generate any states that was ever created before. Okay, so net effects depends on the frequency of loop in the state space. Okay, the more loop include in your state space, okay, the longer it's gonna take the time. Okay, all right, So this is just a summary of what we have learned in this module, module 2.1 and module 2.2. Okay, what we have learned, actually we learned all the process of constructing a sequence of action in order to achieve the goal given by the problem. Okay, and then we studied some methods. Okay, and then we also studied the search algorithms, several search strategies, DFS, TFS, DLS, IDS. Okay, make sure when you read the questions for your exam, read make sure that you are not confused with the algorithm that we ask you to answer for that given problem. Okay, so that's all for our class today. Let me turn this answer.